Thank you. Welcome, everybody. I started at Erlang Solutions last year in May, so just coming up on 1 year. And I had some time on the bench before joining PepsiCo as my current project, and I'm working on their e-commerce platform. And so what this talk is not it's not a practical guide for doing property-based testing, but I've realized that actually would be super helpful. So if anyone wants to prepare that talk and give it, I would appreciate attending it as well. Maybe I'll work on that myself. But in that bench time, I was just exploring open source libraries that I could contribute to. And for each Elixir library that I read about or used, I looked at their open issues on GitHub just to see if there was something there that I could contribute to. And stream data was one of those libraries that I looked at. And I found this bug, or not bug, but feature request that said test shrinking. And one of the suggestions there was add a function named shrink. So I naively interpreted this as a request to add shrinking to stream data. I don't know if you've ever done that, but sometimes you just completely misread something and run with it. So I went off down the rabbit hole of researching how do you implement shrinking for property-based testing. And I found this amazing video of a talk by a guy named Martin Janaszek, and I was going to refer you all to it so you could watch it later for the background on what I'm talking about. But YouTube says the video isn't available anymore and go home. And I thought that was kind of rude, but anyway, what are you going to do? We wouldn't have had time to stop and watch the video right now anyway, so I'm going to summarize it for you. And most of the rest of the descriptions in the next several slides are just taken straight out of Martin's talk, where he covered the 3 forms of shrinking for property-based testing. But a little bit of background. So who is familiar with property-based testing? Okay, it seems like a good majority. But for those of you who don't know what that is, it's kind of a subset of unit testing, but it comes at the process from a different direction. So with unit testing, you come up with example test cases that ensure that your system follows the set of rules that you want it to follow. With property-based testing, you first come up with the rules, and then you use generators to give random values to your system to make sure that those rules are being followed. And the rules are called properties, thus property-based testing. And an analogy that I came up with actually yesterday when I was talking with someone, I think at lunch, that if you think about coming from an object-oriented programming background into functional programming, you just have to think about how you're solving problems in a different way. And so I actually think it's kind of similar coming from traditional unit testing over to property-based testing. You just have to think about your problem or what you're testing just from a different direction. And so just how this works is you've got a generator and you've got a random value that's generated, and you feed it into your test, and then whenever it finds a case that causes the test to fail, then there's a process of shrinking where it takes that huge amount of random data that caused the test to fail and minimizes it down to the smallest, most human-readable example that it gives you of here's why your test fails, or here's the case where your test fails. So you don't have to wade through the massive amount of random data that it actually found the failing test case for. And so there's 3 forms of shrinking, and we're going to dive into what those are. So the first form of shrinking is based on the data type. And this was used in the first generation of property-based testing libraries, which were mostly written in strongly typed languages. So this shrinker really only knows about the data type of the values. And so if we have a generator that produces integers, and then we're interested in multiples of 100, and so we map that to a function that multiplies that by 100. And then our test is that for every n, we're going to assert that n is less than 321. So if we get a 9, and then we multiply it by 100, we get 900, and of course that's going to fail the test. And so then our shrinker only knows that that's an integer. It doesn't know anything about the logic of the generator. And so it might try 450, which was 900 divided by 2, and then it might, subtract 1, or however it's going to find a minimal value, all the way down to it finds 321, and it reports on that. It says 321 is not less than 321, which is true, but 321 is not a value that our generator ever would have produced, so it's not really very helpful. So that leads us to the second form of shrinking, and that uses a lazy tree. And so the generators, in this form, the generator is created as a lazy tree. So if the integer was 3, then it knows how to formulate smaller values in that tree. And then if it was mapped to the multiples of 100, then the tree would look like this. And so back to our example, if we had 900 as the failing test case, and we use this lazy tree shrinker, then it's going to try those values that are down in that tree. Like if it tries 500, then it's going to loop back around and try something else again. And get down to 400, which is actually the value that is meaningful for us, because that's something that our generator would have created, and it's the smallest value that is not less than 321. So this works, and it's an improvement on the previous form of shrinking. But the logic that's encapsulated in the generators are outside that shrinking loop. And so a lot of times you have to write extra code to actually get it to shrink properly. So you write your generator and you think you're done, but no, you still have to add extra things in there to get it to properly shrink. And it also can have trouble with shrinking lists of longer lists of values. So that brings us to our third form of shrinking, and that is what we call internal shrinking. And the way this works is it keeps track of the random numbers that are fed into the generator. So if we don't have any pseudo-random number generator history, then we just give it random values, and the generator will consume those values or consume those random numbers and produce values based on those. And its output is a tuple of the value along with the history of random values that were used to generate that value. And that's fed into the test. And then, instead of shrinking the value, we shrink the random numbers. And we do that in a uniform way so that any generator that is built on top of our random number history model will be able to it will produce smaller values with smaller random number history. And we'll look into a little bit more how that works. But putting the generator and the generating values inside the shrink loop ensures that all the guarantees of the generator are kept. So this generator is impossible for it to create values, shrunk values that it wouldn't have randomly picked if it got lucky anyway. And this form of shrinking was first implemented in Python in a library called Hypothesis. And here's a quote from the guy who originally created that. His name is David McIver. He says, "Hypothesis takes the shrinking outputs can be done by shrinking inputs, and it takes that idea to its logical conclusion, and has a single unified implementation or intermediate representation of all generation is based off of." So wow, this is great. All property-based testing libraries should use this form of shrinking. So then I came back to stream data, and of course realized, oh, actually it does have shrinking. It was silly of me to think it didn't. And the shrinking that stream data uses is actually that lazy tree form of shrinking. And that property of multiples of 100 being less than 321 shrinks just fine in stream data. It does okay. But this was another issue in stream data, and actually I'm going to switch to the web view of that, if I can find my mouse. Okay, because this was longer than what would fit on a slide. So the example output that it was creating, basically what it's doing, it's got this white test or this white list, and the function that it's testing basically takes the fields and filters out the ones that aren't in the white list. And the actual issue here was that the garbage fields sometimes could be values that were in the white list, so that would cause the test to fail. But if we look at this clause here, the real values are here. And then if we look at what it actually reported, it didn't shrink that list of real values down at all. It's just the same values there. But the minimal counterexample, like what we would really look for if shrinking was being done right here, would be the whitelist would be the atom of the capital letter I, and garbage would contain a string with the capital I. And that's all we need to know, like what the actual problem here was that we should have been shrinking. So if we come back to slides. And so when I saw that, after having watched the video of Martin's talk, I was like, oh, this could have been a slide in his presentation. Like this was an example that he used of when traditional forms of shrinking didn't work. And one of the things, so I was like, this is great. Has anybody tried implementing it in Elixir? Well, I couldn't find any. So one of the things Martin mentioned in his video was, hey, if anybody wants to implement this form of shrinking in another language, I'll help you. And definitely his help and insights have been invaluable for doing this. And the first thing I thought about was, could we just swap out the shrinking that stream data uses? And actually at Codebeam in Berlin last year, I talked with Andrea Leopardi, the author of Stream Data, and he said he'd be happy to swap out the shrinking of Stream Data if we didn't have to change the API. But that's where it kind of, I didn't see a way forward of doing that, because in Stream Data there was no mechanism to get back the PRNG history. And we also didn't really need the lazy tree that was no longer needed. So I decided to build my own library just as a proof of concept to see that this would work. And even though it was only a proof of concept, I spent some time coming up with a name, so I call it decorum. And the dictionary defines this word as propriety, which if you squint a little bit and maybe throw in a little bit of dyslexia, that kind of looks like property. And then it also is defined as a requirement of correct behavior in polite society, which sounded like a great name for a testing library. And the tagline I came up with is property-based testing for Elixir with shrinking that just works. So the first thing I implemented was the PRNG struct, and it's basically a wrapper around the Erlang rand module, and it has two states. So its random state just uses rand to generate new values that it stores in history. And then the hard-coded mode is used to replay the previously recorded or simplified history. We represent the random values as 32-bit non-negative integers because those are easier to work with when we're shrinking the history. And it's what the other implementations of this shrinking have also used. A side benefit of having that ability to replay hard-coded history made testing the generators and functions like map and filter actually very easy. So then I came up with a whole bunch of questions of like, where do you even go from here? How do you create a property-based testing library, and what do you need to do? And it re-emphasized the fact that there's nothing like trying to implement something to find all the ways that you don't understand it. And I had a ton of questions, starting with like, how does XUnit even handle random numbers and the seeds? Like, y'all know you can replay tests in XUnit and give it a seed, but like, what does it do with that? And how do those even work? And I had a bunch of other questions as well, which we don't really have time to go through all of those. But we will look at a few of these. What time does this session end? Okay, okay, cool. I gave myself timing, but I didn't. I should have given myself clock time for this. So what is a generator? So a generator in Decorum is a struct. So there's a Decorum struct, and its only property is this generator function. And what that does is it takes the PRNG struct and returns back a tuple, which is the value and the updated PRNG struct. And that, if you're in random mode, it's just appending the next random number that it used to the list. If you're in history mode, it's keeping track of where you are in the replayed history. And so I wanted to replicate the way stream data uses generators to produce streams of random data. And the first way I tried that was with the Elixir stream module. And it has this function called unfold. And it takes an accumulator and the next function. And the signature of that next function exactly matches our generator function. It takes an accumulator and gives you back the next element along with the updated accumulator. And this worked great. It helped me get started. I was able to test a few of my early generators that I created. But there was actually an easier way to consume the generators. And that is actually implementing the enumerable protocol. And I borrowed this straight out of stream data. In spirit, Decorum is a fork of stream data, even though it was starting from scratch, because I borrowed a lot of things of how it worked. But any struct you have can implement the enumerable protocol and then also be used for any of the functions in the enum module. And most of this is boilerplate. The one function clause that's really important here is the final reduce, which actually calls our generator function. And all the rest of it is just kind of what the enumerable protocol needs. And it can, if you have a struct that count is meaningful or member is meaningful or slice is meaningful, you can also implement those. But if you don't implement those, all the functions in the enum module can run if all you implement is the reduce. So this was, right, that's all I was gonna say about that. Okay, here's an example generator. And this one is called uniform integer. It's not truly uniform, but it doesn't really matter. It generates integers between 0 and the given max. So the new function there is just a helper to create the Decorum struct that uses this generator function. So it calls PRNG next, which just gets the next value, either random or hard-coded value, depending on what mode we're in, and then uses the remainder function on that value to give us the value that we're looking for. So we're going to demo this. So one second while we switch modes again here. So I've got the IEX shell running in Decorum, and if we call that uniform integer and give it a max value of 5,000, and because it's a stream, if we didn't do a take there, then we would just get an infinite stream of those random values. So we take 20 of them and inspect the values, and we see we've got some random integers, which is great. And we can run that again, and so we get different random integers. And then we've got an atom generator, and we can run that one. And all of you should be freaking out right now because of what this is about ready to do. And if you don't know, it'll be evident here in a few seconds. And and note to self, I need to add a caveat in the atom generator of like, be careful how much you use this. Because there we go, crash dump. We created too many atoms. And so yeah, that's a fun one. All right, back to slides. Which, I mean, that same thing would have been true for stream data as well. So then we want to talk a little bit about generating lists, because it's actually kind of surprising how many other generators are based on lists. So binary and atom and string are all internally use the list generator, which basically takes another generator and just creates a list of values from that generator. So traditional method of generating a list, you would pick a random count and then generate that many number of elements. So if you got a 3, then you'd then you'd take 3 more random values, 97, 98, 99, and that would give you the string ABC. But when we're shrinking the random values that are fed into creating the list, shrinking that 3 along with how many elements come after it would not, especially for longer lists, those being farther apart in the random number history would be harder for our internal shrinking to handle. So what we actually do is we used a biased coin flip to determine if we're going to produce another value or not. So if we get a true, then we generate the 97, and then if we get a 1, then we get the 98, and then we get another 1, and we get the 99, and we get a 0, so we stop. We're done with the list. So that creates that same string ABC. And when we have the random number history that looks like that, then one of the steps of shrinking that random number history is just deleting values. And so we can delete pairs of values out of this random number history, and it doesn't really mess with the generator of our list that's consuming those values. And then the other way that we shrink history is a binary search on each value within the random number history. And I really wanted to draw this out and go through, run through a whole example of how this works, but I had to cut that because of how short these sessions are. But basically, if we were gonna run through this and shrink that value 98, we would take 0 as the low and 98 as the high, and then test the midpoint of that. And if it was still an interesting value, and then we had to feed that back into the whole list because our generator needs that whole list of random number history to produce meaningful values. So we stuff that back in the list, and if the test still fails, then we keep that mid as our new high. If the test passes, which means that value's too low, it's not interesting, then we keep it as the new low, and 98 stays as the high. So that's kind of the internal implementation of how that shrinking works. And as I mentioned, it loops back into the generator. So we discard values that either, sometimes we could run out of history or the test passes, so it's not an interesting result. And we just go until that history is as short as possible and the values are as small as possible. So after all of that, did we fix the bug that stream data had? A month ago, I gave this talk at the Stockholm Beam Languages meetup, and I had to say no to this question, but I still kept it in the presentation for the laughs. But now we have done that. So here is the side-by-side stream data test and the decorum test. And I put this in a new library where I put both of I brought both of them in as hex packages. So the stream data test is pretty close to what they had in the bug on GitHub, but I cleaned it up a little bit. I took out a couple of the things, but in decorum we don't actually have macros yet, but as actually the API works pretty close even without the macros. And then we also don't have clauses. So if you look at line, oh no, I don't have my glasses. Line 24, the check all, the next 3 lines, 25, 26, and 27 are generators that you can pass into that macro in stream data, and it will make all of those values available to your test. So in decorum, without that, we use the zip function on the right-hand side, line 20. And that just works exactly like an enum zip. It takes a list of generators and gives you a tuple, or it gives you a generator that's the tuple of the values out of that pair of generators. And so now we can show this actually running. Okay, so here we have the output of the decorum test, and on the to-do list is like cleaning this up and better error messages, but it found the small test case of the capital letter D as an atom and the string D as the minimal test case. But of course, the stream data is this, like the red is like the original value it found, and then the assert. And as we mentioned, this would be a huge amount of data to look at to try to figure out why your test was failing. Where are we at? Okay, so all right. Oh, and the other benefit of this is that we have tested shrinking, which was that original GitHub issue of a feature request for stream data that we test shrinking. So because all generators use the same form of shrinking, we test it and we validate that it works, and it should work on any generator. So here's another quote from the creator of Hypothesis. And this is out of a paper where they kind of give like all the academic reasons of why this works, if you're interested. So the key idea of internal reduction is to manipulate the underlying source of randomness consumed by a random generator in order to cause the generator to produce smaller test cases automatically. And the final reduced test case is constructed as if the generator had been implausibly lucky and produced a small readable test case by chance. So while I was preparing this talk and that demo app of comparing the tests, I ran the tests a bunch of times to find what seed I wanted to use to show the example. And I discovered something that actually surprised me. There's a seed that you can use with that demo project that causes stream data to give a small readable example. So this is that stream data test failing, and it's just the lowercase r example. So it was kind of a surprise, but it kind of proved the point from that quote that but trying all the different possible seeds to find a small example would not really be practical. So next up, where do we go from here? So adding more built-in generators, there's a whole concept of well-shrinking float, which I don't even have time to touch on. But outside of that, pretty much any generator that you use or build on top of the existing primitive generators should work without any concern for how they shrink. But any examples of properties that don't shrink well, we're going to treat as bugs to be fixed. And then we need to add the macros and showing better test failure messages. And then potentially also revisit integration with stream data. But use it if you want to. I'm open to contributions, suggestions for better ways of implementing any of this. And then I mentioned Martin a few times. If you happen to be attending Lambda Days next month, he's going to be giving this talk on property testing all the things, which might actually be close to that talk I mentioned in the beginning that we need to see. So I'm looking forward to catching the video on that one. And then here's resources, links to Martin's GitHub and his talk at Lambda Days, Hypothesis, the original implementation, and then my test packages. So thank you very much.
Thank you, Dennis. We have time for one question, if anyone has anything.
Thank you for the talk, really insightful. So if somebody wants to do similar work to you, where would you recommend them to start?
Similar,
maybe
in
a
what way?
different project, maybe built on top of yours?
Ah.
Or maybe books that you found the most sort of useful to learn about these things?
That's a good question. I mean, really, this might be a more generic answer than you were looking for, but for me, it was pursue what you're curious about. like I spent some time, as I mentioned in the beginning, I looked at lots of different libraries and what their open issues were. I actually spent a little bit of time on Phoenix LiveView and contributed one bug fix in LiveView. And so, like, just following your curiosity, and if you find something that you don't know how it works, like, try your hand at like writing something similar, yeah. And open source maintainers are very, for the most part, are willing and open to accept contributions. Chris McCord was great to connect with on LiveView, and he's actually told me he doesn't have as many contributors as he would like. So I think there's it does take some effort to kind of push through the figuring out what the system needs and how you can contribute. But yeah, just following your curiosity, I think, is the biggest tip.
Thank you, Dennis.